A very good morning to all my dear students. Sage Anandam. So we'll covering the all the topics of analog and digital communication in the series of our lecture series, YouTube lecture series. So this is my first lecture series, first lecture of my lecture series, covering the topic of amplitude modulation. So let's discuss first about modulation. So what is modulation? It is the variation in the amplitude, frequency, or phase of the carrier signal in accordance with the instantaneous amplitude of the masses signal is known as modulation. That means we will be varying either the amplitude, frequency, or phase of the carrier signal. What is the carrier signal? Now the carrier signal is a high frequency sinusoidal signal which is added to the masses signal, that is known as modulation. So the modulation is adding information to a carrier signal and the information is carried in the masses signal. So this is the basic block diagram of our modulation. So what we do in the modulation is a baseband signal. Now what is the baseband signal? A baseband signal is basically an electrical form of signal. The masses signal is either in the audio or the video form, which is first transformed into the electrical form. This electrical form of signal is known as the baseband signal. That is the modulating signal. It is combined with the high frequency carrier signal in a modulator, and the signal which is generated by the modulator is known as the modulated signal, which is then transmitted through RF amplifiers. So why do we need modulation? As we know, to transmit a voice signal, a large size of antenna is required, and the antenna length is proportional to half of the wavelength. So the size of the antenna will be more than the distance between the transmitter and receivers. That's why a high frequency carrier signal is taken, which can travel a long distance without attenuation. And due to high frequency, smaller antenna is required. This is the basic classification of modulation. We'll covering all these modulation techniques in the upcoming lecture series videos. So going through one by one, first is the continuous wave modulation and then pulse modulation. Then the continuous wave modulation is further divided into two, that is amplitude modulation and angle modulation. Our first lecture is on amplitude modulation. Angle modulation is further divided into frequency and phase modulations. Then in pulse modulation, we have two classifications, analog and digital modulation. In analog modulation, we have pulse amplitude modulation and pulse width modulation and pulse position modulation, that is PAM, PWM and PPM. And in digital modulation, we have pulse code modulation, PCM and DM, that is delta modulation. So first coming to the amplitude modulation. So in amplitude modulation, as I have already told you, what is modulation? Variations in the three of its categories, either amplitude, phase or frequency. So amplitude modulation is the process of varying the amplitude of a high frequency carrier signal in accordance with the instantaneous amplitude of the modulating signal. This is also known as double-sided band full carrier modulation. Why it is known as DSBFC, I'll tell you in a couple of minutes in this video lecture only. If MT is denoted as the masses signal and the carrier signal is given as CT is equals to A cos omega CT, where omega C is the frequency of the carrier wave. Then the AM signal, which is denoted by FT, is written as FT is equals to A plus MT cos omega CT. This is the basic waveform, how the modulation takes place. Suppose this is our masses signal, whose amplitude is given as AM. It is the instantaneous amplitude of the masses signal. AC is the instantaneous amplitude of the carrier signal. This is high frequency carrier signal. When these two are mixed with the modulator, then this type of wave is created, where the upper portion is known as the envelope, which is the masses signal. This arrow, as the arrow is moving, this is the envelope. This is known as envelope, which is same as the modulating signal, masses signal. And inside that, a carrier is transmitted. Carrier signal doesn't carry any information. The whole information is carried in the masses signal. The carrier is only to carry this information from transmitter to the receiver. So this is the frequency spectrum. It consists of three. It is described in the next slide, but I'll tell you the here only. I'll discuss with you here. It consists of three components. First is the carrier component, FC. FC is the frequency of the carrier wave, the upper sideband and a lower sideband. Upper sideband has a frequency carrier of FC plus FM. That is the addition of both the frequencies, frequency of a carrier and frequency of the massive signal. And the lower sideband is the difference of both frequency of carrier and the frequency of massive signal. The bandwidth is given as upper sideband minus lower sideband. So it comes out to be twice of FM. That is twice of frequency of the massive signal. As I have told you, it consists of three components: a lower sideband with highest frequency component of FC minus FM, an upper sideband highest frequency component of FC plus FM, and a carrier frequency. Now, as I have told you that it is known as double-sided band full carrier. Why I have told you? Here it is, as it is containing two sidebands, upper sideband and a lower sideband. So double sideband with the full carrier. That is why it is known as double sideband full carrier modulation. I think now it is clear why it is known as this. Now, based on this frequency spectrum, it is further, amplitude modulation is further divided into four. First is double sideband full carrier, which is simple AM. Okay? This is a standard AM used for broadcasting. Hence, the carrier convey no information. As I have already told you that carrier wave contains no information. The whole of the information is contained in the envelope, which is the massive signal. Modulated wave envelope has same frequency as the information signal, as we have seen in the waveforms. Amplitude of the modulated wave varies according to the amplitude of the information signal. That's why it is named amplitude modulation. This is the basic waveform of a DSB FC, which is same as AM signal. Now, coming to the advantages, transmitters are less complex, receivers are simple, so the detection is easy. Receivers are cost efficient. DSB FC waves can travel a longer distance, have lower bandwidth, but have twice of FM. Disadvantages: power wastage takes place as two sidebands and one carrier is transmitted. So power is wastage. DSB-FC needs larger bandwidth, twice of FM. DSB-FC wave gets affected due to noise, and the applications are radio broadcasting, picture transmission in a TV system. Now coming to the second type of amplitude modulation, which is double sideband with suppressed carrier. As I have already told you that carrier does not carry any information. So receiving it on the frequency spectrum is a limitation. So if we suppress the carrier, no information is being lost. So here in this, the carrier wave is absent. So all the transmitted power is contained in the lower sideband and the upper sidebands only. So only two sidebands are transmitted. Here, frequencies produced by AM are symmetrically spaced above and below the carrier frequency, and the carrier signal is reduced to the lowest practical level, ideally being completely suppressed. This is the basic waveform. This is the massive signal. This is the carrier signal. And this is how DSB-SC waveform looks like. As the carrier is suppressed, so here is almost zero. Then coming to the third, that is single sideband with suppressed carrier. As the same information is carried in two sidebands, that means we are transmitting the copy of information. One is original, one is the copy. So same information is being transmitted twice on a single bandwidth. So this is a big limitation. So we can suppress one band and we can transmit it. So this type of technique comes under single sideband suppressed carrier. In SSB-SC, either the upper sideband or the lower sideband contains the complete information of the massive signal, and only one sideband is necessary for information transmission. This is how the waveform looks like. This is the spectrum of a massive signal. This is the spectrum of double sideband with suppressed carrier. Carrier is not present over here. Okay? Only two sidebands are. So these two are the frequency spectrum waveforms of the SSB. Either only the upper sidebands or only the lower sidebands are transmitted. Coming to the advantages, lesser bandwidth than DSB-FC, lots of power saving, as the power saving is half, reduced interference of noise. The bandwidth of SSB is only FM, not twice of FM, only because only one sideband is carried. Okay, and the bandwidth of DSB-SC, double-sided with suppressed carrier, is again twice of FM. Why? Because there only the carrier was suppressed And bandwidth calculation, carrier does not take part. Only the sidebands take part. Okay. Disadvantages of SSB. The generation and reception of SSB signals is quite complicated and needs an excellent frequency stability. Applications. It is used in land and air mobile communication systems, in telemetry and military communications, and in navigation and amateur radios. Then last is the vestigial sideband suppressed carrier. In this, only either USB or LSB is transmitted. This is the modified form of SSB, single sideband, but a partial part of the other sideband is also transmitted, as designing of filters of transmission and reception of SSB is very difficult. So VSB was designed. So only a partial part of other sideband is also transmitted. Let's discuss in detail. The limitations of SSB modulation being used for voice signals are not available for video or TV signals, which leads to the usage of vestigial sidebands. A vestigial sidebands in radio communication is a sideband that contains one full sideband and a partial other sideband with suppressed carrier. So this is the basic waveform diagram of the frequency spectrum diagram of VSB-SC. This is the spectrum of the massive signal. Here, full USB is transmitted and a partial part of LSB is transmitted, not the full. Okay, students. So coming to the advantages, it is a reduction in bandwidth. The bandwidth will be slightly greater than SSB, but less than DSB-SC or DSB-FC. Easy to design its filters. It has a good phase characteristics and makes transmission of low frequency components possible. Applications, it is used in transmission of TV signals because the video signals need a large transmission bandwidth if transmitted using a DSB-FC or DSB-SC techniques. Comparison of various amplitude modulations which we have discussed till now, it is converted to a tabular form which is easy for students to learn. Carrier suppression in DSB-FC doesn't take place. In DSB-SC, it is fully compressed. SSB, it is fully compressed. And as VSB is the modified form of SSB, so it is not applicable because the carrier is already suppressed here. Sideband suppression, here it is not there. One sideband is completely suppressed, and here one sideband is partially suppressed. Bandwidth is twice FM of both the DSBs, and it is FM, and for VSB it is greater than this but lesser than these. Transmission efficiency is discussed here. Number of modulating inputs are discussed, and applications we have already discussed. So I think that's all about amplitude modulation. In the next lecture, we will be discussing about the amplitude modulation, modulators and demodulators, which is again a very important topic. If you have any queries related amplitude modulation, which we have discussed till here, please let me know in the query. Please continue with the next lecture also. Thank you. Sej Anandam.